Now, I'll go easy on you for this, because it is the first example where, do you see what I mean by, now Extension 1 students, you can momentarily tune out if you like, because Extension 1 students will never get a question that just says that. Okay, just by itself, that's the question. However, this could appear like something like this that's simpler, could appear within an induction proof, but it's not going to appear by itself. Now, I'm going to go easy on you. I'm not going to expect, like I've given you a whole, like by the way, when I learnt that all those properties I listed off for you, I learnt them as a list of like 15 separate things, and I was like, what do any of these have to do with each other? So I've sought to try and show you how they relate to each other. That's what the category is about. I'm not going to expect you to see this and think, I know exactly what category to go for. It's actually got a bit of a red herring in it, which is also why I'm going to use this example with you. So what do you think is the obvious red herring?
We already know that A minus 1.
The obvious red herring is, by the way, if you don't know what a red herring is, it's a false clue. Is there a reciprocal there? Okay. So I see a reciprocal, so I think, are there going to be reciprocals involved?
The reciprocal.
There are not really. Yeah, the reciprocal category. I'm not really going to be able to use the reciprocal effectively because I need two reciprocals, basically. And you can take reciprocals at both sides, but it ends up just being an algebraic disaster. So I'm going to start with something else. I'm going to say, no, and I'm going to use one of the properties that I already know with a particular value. Okay, now you're thinking, okay, yeah, all right, I'll tell you in a second. You're thinking, how did I know to go there? And the answer is, I didn't know immediately, okay, but I've got some experience with these now. One of the clues was this guy here, right? He's sort of floating there, and you're like, what is that about, right? It's easy to prove something positive, easy to prove something's negative, but where does he come from? And the answer is, he comes from combining these in a particular way, right? And it has to be to do with squaring. Squaring comes up like 95% of the time with inequalities, because squaring tells you you're this way or you're that way. Have a look at the left-hand side. Let's expand this there, okay? What happens when you square this? A. What happens when you do the minus 2ab bit? It's just going to be minus 2.
Oh, perfect.
Oh, look. Oh, really? That was it? It looks so intimidating because you didn't have the lenses to see, well, what am I supposed to use in this case, right? So here it's just a pretty trivial addition, right?
Can you the reverse thing? To say no, A minus 1 squared is greater than 2.
Yeah. Sorry, say that again slower.
What you did, but instead of that, using this whole thing squared is greater than
A minus what thing?
1.
Oh, A minus 1 all squared,
Yeah.
and then divide through. Yeah. Yeah, that would work. The reason you can do that is because it's positive. It's fine. This just gets me there faster. Okay. Now, remember I said to you before, hey, you can also do a proof by contradiction. A proof by contradiction. So let's assume, here's a second way to do it, right? This is proof by contradiction. With inequalities, it's really nice. They're set up nicely for proofs by contradiction. Because actually one of the trickiest things with a proof by contradiction is knowing what is the exact opposite of what you're talking about. Okay, so I'll give you an example. If I say to you, a number is a number is even, you might think, the opposite of that is the number being odd. But it's not true, right? Because a number can be neither even nor odd, right? 0 is an obvious one, but there's kind of a lot of other numbers that are neither even nor odd. How about all the numbers between the numbers that are even and odd? Like all those infinities of, like, say 1.5. Is 1.5 even or odd?
Oh my god.
And the answer is it's neither of them, right? So you got to be careful. You can actually do those, by the way, but they're not called proof by contradiction. They're called proof by contrapositive. You can go look it up if you're really curious about it. However, an inequality is set up perfectly for a proof by contradiction because you can very easily state the exact opposite of this. You can say, assume that in fact it's not greater than or equal to 2. Assume that it's less than 2. Okay, assume that it's less than 2. Now, if this is the case, well, what would you like me to do? Let's just let's go with what you guys suggested to me before. I think I can I do it? Will that be a bit tricky? Yeah, I can do it. Okay. So what you guys were suggesting before is to take advantage of this property, which means I can multiply through by this number because it's positive and it preserves the inequality. So I'm going to say this. Okay, I'm multiplying everything through by a. Yes. Okay. So then I'm going to subtract like this. Okay, so what am I going to do with the left-hand side now? What is that? Okay, so this is actually a take away 1 squared. Uh-oh, I'm in a problem, right? I can say, but, a take away 1, that's the thing being squared, it's a real number. Because a is a real number, so subtracting 1 doesn't take it out of the real field, right? It's still a real number. So if it's a real number, that can't be the case, right? So therefore, you have a contradiction. And just for lols, I always write contradiction with an exclamation mark, okay? So it's like, no, this clearly can't be the case. Ridiculous. So therefore, your assumption, assuming all of your logic here is sound, right? Therefore, your assumption must have been wrong. So therefore, a plus 1 on a is not less than 2. And the only way for it to be not less than 2 is if for it to be greater than or equal to 2. Okay?
That seems a bit dodgy.
And perfectly sound.
Like, so from that, how do we know